we have come to the last annotated PowerPoints for the muscles, so it's time to just kind of clean things up and look at a few leftover topics. We certainly have covered mostly, how muscles actually contract, where they get their energy, how you generate different amounts of contraction, a muscle force. So we have a handful of topics now to just kind of clean up here. So in isotonic contraction, the muscle length changes. So this is sort of typical muscle contraction. If you're doing like curls at the gym, your biceps brachii starts off long, and as you curl that weight, your biceps brachii becomes shorter. If it changes in any way, or if the muscle length changes in any way, that's called an isotonic contraction. When the muscle gets shorter, that's called concentric. That would be most typical. But also, you can be contracting a muscle as it gets longer. So imagine now you've curled the weight. Think about now as you let the weight back down, your muscle is still contracted, but now the muscle is getting longer as you let the weight go back down again. You're still having to use muscle contraction to hold that weight up, but it's just that as you let the weight down, the muscle is now lengthening instead of shortening. So that's called an eccentric isotonic contraction. So do you get it? Two kinds of isotonic contraction. In both cases, the muscle is changing its length. If it's getting shorter, that's concentric. If it's getting longer, that's called eccentric. And then there's another possibility here. In isometric contraction, the muscle length remains the same. So if we were in the classroom, I would go over and I would try to move the wall of the room. And when I try to move the wall of the room, my muscles are contracted. I'm really pushing hard against that wall. But of course the wall is not moving, therefore the length of my muscles isn't moving, but they're still contracted. That's called isometric contraction. It means the muscle length stays the same. Okay? There used to be a big fad of isometric exercise when you were like sitting at the office and you couldn't go to the gym. Do things like, try to push your desk into the floor. All right? Your muscles are contracted while you're doing that, but they're not changing their length. Or, try to lift your desk off the floor. Your muscles are contracted, but they're not changing length. Unless, you have a really lightweight desk and you're able to actually lift the desk. Delayed onset muscle soreness, DOMS, results from extensive eccentric contraction. Shows up within 24 hours after exercise, like hiking downhill. Hiking downhill, oh my God. I hiked down into the Grand Canyon, and actually going downhill is the most stressful part of the hiking because your legs are lengthening as you go downhill, and so the muscles are lengthening, but they're still contracted. So when you do a lot of that stuff, and you've probably experienced this before, if you're not in terrific shape and somebody cons you into playing with their soccer team or their softball team over the weekend, and you feel okay while you're doing it, and you may feel okay later that day, and then you wake up the next morning and you're like, oh my God, what was I thinking? You try to get out of bed and your muscles are just sore and they ache. That's called delayed onset muscle soreness. Usually goes away within a few days, in my experience, and within a week, I would think. Not completely understood why that happens. May result from damage to the Z discs, remember, at the ends of the sarcomere, and the connective tissue. So, again, it's just a common experience. I'm sure you've had it, and now you know the name for it. DOMS, delayed onset muscle soreness. It's a very natural kind of a thing. Okay, there's a picture of me there, back when I was working out a little more. Then on the right, you see a picture of my friend Jill with those abs, huh? Yeah, Jilly, she's a gym rat. So during embryonic development, muscles grow by hyperplasia, which is an increase in the number of muscle cells. So you're actually adding more muscle cells or muscle fibers to the muscle as you're developing in utero, all right? Once you're born, however, you generally don't change the number of muscle fibers or muscle cells that you have. What can happen, though, is you change the size of each one of those muscle fibers. That's hypertrophy. So that's what happens when you go work out at the gym and you build up muscles. you're not actually adding new muscle cells. You're making each muscle cell larger. That's hypertrophy. And how do you suppose you make the muscle cells larger? Remember what makes up 80% of a muscle fiber? Myofibrils, the contractile organelles. So you're just adding more myofibrils to the muscle. That's hypertrophy. That makes the muscle larger. You're not adding new muscle cells. So keep those two straight, okay? Muscle growth, by the way, is inhibited by myostatin, a natural growth factor. Statin means to stay the same. Like people with high cholesterol take statins to try to keep their cholesterol the same, lower. Tries to stabilize cholesterol. Remember, most of your cholesterol is made by your liver. A mutation in the myostatin gene can produce dramatic hypertrophy. And here you see a breed of cow, and I should have looked this up before I started this. I think that might be called Belgian Blues. I don't know. I'm probably wrong. But at any rate, look at that cow. Looks like it's been hitting the gym, huh? No, it's actually a genetic defect here, in which there's no myostatin, and so or a decreased amount of myostatin. So therefore, the muscles hypertrophy causes the muscles to get larger and larger. So myostatin normally keeps muscles from getting too large. Alright, so types of skeletal muscle fibers. We've talked about muscle fibers quite a bit. But we're going to look now at the fact that there are different basic types of muscle fibers, which I don't think we've mentioned up until this point. Skeletal muscle fibers classified according to structure and function. We've seen that distinction many times, haven't we? Slow oxidative fibers, SO fibers. They're small in diameter, but they're high in myoglobin, so they appear red. You looked at meat before, red meat, steak. Yeah, a lot of those SO fibers. They're least powerful, but they're very resistant to fatigue. So these are the endurance muscles, okay? A lot of myoglobin, a lot of oxygen there, okay? So you can make a lot of ATP aerobically, so endurance. Not very powerful, but again, they don't need to be powerful, they just need to keep you going. So resistant to fatigue, slow oxidatives. Then there are what are called fast glycolytic, FG. These are large diameter fibers. They're very low in myoglobin, and so therefore they look white. They are the most powerful, but they're the most susceptible to fatigue. So, I show the picture there in the upper right. You probably, even if you're a vegan, you've probably seen people eating Thanksgiving before. So, you cut into the breast of the turkey, you got all that white meat, but then, down in the drumsticks, you got all that dark meat. Alright, what's going on there? What kind of muscle fibers do you find in the white meat of the breast? Would those be SO or would those be FG? Right, those are FG. So notice those are large diameter fibers, low in myoglobin. They're powerful but susceptible to fatigue. What do turkeys use their breast muscles for? Yeah, basically all birds. What do they use those breast muscles for? Flying, flapping those wings. Have you ever seen a turkey fly? Man, that's a lot of weight to get airborne, okay? So they really have to get them things flapping. So you need a lot of power in those breast muscles, all right? Get that turkey airborne. But are turkeys known for being able to, fly all the way across the ocean? Like the Arctic terns or whatever? No, they don't do that. I forget who flies all the way across the ocean. But, they tire out quickly. Turkeys can't fly for very far, all right? But then think about, the drumsticks. Think about there. What do turkeys do, with their legs? They just kind of, that's chickens, but, turkeys, same basic things. All they do is they just walk around all day. So, you don't need a lot of power in those muscles. You just need them to work for long periods of time. That's why you have the dark meat in the thighs and in the breasts. And what you're seeing there is basically a lot of fibers that are high in myoglobin. That's the dark meat, okay? So you've seen it before, you just didn't realize that's what was going on, maybe. There's also an intermediate form, the fast oxidative glycolytic, the FOG. Those are just intermediate between the two. I don't really care about those so much. I mostly want you to know about the SOs versus the FGs. Most skeletal muscles are a mix of these fibers and about 50% SO. So in other words, all of the big muscles in your body, they need to be able to be versatile to do various things. So you want a mix of fibers, so you can do some aerobic type stuff, and also you can do some powerful type stuff. So generally speaking, remember recruitment. You're going to recruit the SOs first. They're not very powerful, but they have endurance. If that won't do the trick, then go to the FOGs, then go to the FGs. Keep recruiting muscles that are more and more powerful to get the job done. And different training regimens can change the proportion of these types. So marathon runners and endurance athletes generally tend to have a lot of SO fibers. I saw a guy, they have these super marathoner people, the ones who do like these 48-hour races or whatever. They run nonstop for like a couple hundred miles or whatever. I've seen they had a super marathoner, and they had this guy, they told him like to sprint, and his sprint was like slower than your sprint. I mean, he's a world-class athlete, but you can outrun him for 20 yards or whatever. But yeah, just try for 200 miles and he's gonna wipe you clean. So yeah, endurance athletes, Tour de France cyclists, they have a lot of SO fibers. Those guys don't look bulked up, do they? No, they have remember the SO fibers, small in diameter, all right, not very powerful but highly resistant to fatigue. Whereas power lifters and sprinters, those are the people that really look sculpted, don't they? Those are the people that really need big, powerful muscle fibers. So they have a lot of FOG and FG fibers, and they look it. You can tell. They look different. They're all bulked up. They need more power to do what they're specializing in. So which would you expect to find in the extensor digitorum and flexor digitorum superficialis of a classical pianist? Mostly SO fibers and small motor units, mostly FG fibers and small motor units, mostly SO fibers and large motor units, mostly FG fibers and large motor units, or E, which is the throwaway and isn't definitely the right answer. So what do you think? Classical pianists, what are they doing? Are they sitting there, just pounding at the keys with powerful movements, or are they using fine, delicate movements to tickle the keyboard, as they say? Yeah, so they would have mostly SO fibers and small motor units. They're doing delicate, precise contractions of the muscles of their fingers and wrists. Whereas, again, if we were talking about a power lifter or something, those people would tend to have big motor units with FG fibers. So we talked about skeletal muscle. That's what we've spent all of our time on so far. I need to say just a few things about smooth muscle. We mostly talk about smooth muscle in Bio 202 because smooth muscle, remember, where do you find smooth muscle? In the walls of arteries, in the airways, all right, in the bronchi that go to the lungs, and then also in the linings of the walls of your internal organs. So Bio 202, when we cover cardiovascular and digestive and respiratory and so on, that's when we talk a lot more about smooth muscle. So smooth muscle, in contrast to skeletal muscle, smooth muscle has only one nucleus per cell. It's not multinucleated, all right? Remember, the skeletal muscles were formed from a bunch of myoblasts that all fused together. Not so with smooth muscle. No striations, all right? So you don't have those overlapping thick and thin filaments to create the striations. There's endomysium only, no tendons with smooth muscle. Has a much smaller sarcoplasmic reticulum, remember, which is where calcium is stored. And it has no sarcomeres, again, no thick and thin filaments overlapping, has no myofibrils, has no T-tubules, all right? So it doesn't work that way at all. So it's very different. Remember, skeletal muscle and cardiac muscle were pretty much similar. Cardiac muscle looked like skeletal muscle, except that all the fibers were branched and interconnected. Smooth muscle is really a completely different type of muscle. It has these pouch-like folds in the sarcolemma called caveoli, not ravioli, caveoli, that sequester calcium. So that's why you don't have to have the sarcoplasmic reticulum are much smaller. So you've got all these little pockets of calcium, these caveoli all over the place. So you still need calcium, it's just that you supply it in a different way. And smooth muscle has two basic types of fibers. The longitudinal contraction dilates and shortens the muscle, and the circular contraction constricts and then lengthens the muscle. So we'll see this in Bio 202 when we get to the intestine, for example. The circular muscles contract in order to mash up the food, because that's part of what your stomach and your intestines do. They literally mash up the food. But then we also have to make sure that we move food from the entrance to the exit. So that's called peristalsis. And peristalsis is a wave of contraction that moves things, from, remember your gastrointestinal tract is a 30-foot long tube that runs from mouth to anus, all right? It's one continuous tube. Think about that. When you kiss somebody, you're making a 60-foot long tube that runs from butthole to butthole. Remind somebody that the next time you kiss them. Say, hey, babe, let's make a 60-foot long tube that runs from butthole to butthole. But so you have to move things towards the exit. That's part of what digestion means. You have to get the nutrients you need, but whatever you can't need, you got to get it out. So peristalsis is the wave of contraction that does that. So it's the longitudinal fibers that cause the peristalsis, and then the circular fibers cause the actual mashing up of food. All right. Where do you find smooth muscle? In the integumentary system, those are rector pili muscles. In blood vessels and airways, regulating blood pressure and airflow. So one of the main controls over your blood pressure is the dilation and constriction of blood vessels. When you constrict a blood vessel, it makes the diameter smaller. That raises blood pressure. When you dilate a blood vessel, that reduces the blood pressure. When you dilate a blood vessel, it makes the diameter larger, lowers blood pressure. That's one of the main ways your body controls blood pressure. And in the reproductive and glandular system, producing movements, so secreting fluids, secreting enzymes and things like that, hormones. All right, so muscles do the contraction to do the secretion, and in the digestive and urinary system, forming sphincters and producing contractions. Okay, so smooth muscle, very important. Just we're going to talk about it mostly in Bio 202. So looking a little bit more at the way smooth muscle is put together, no neuromuscular junction as in skeletal muscle, but what are called varicosities that release neurotransmitter into diffuse junctions. So look in the upper right. Notice it looks like sort of like synaptic knobs, but they're not. They're all connected together. Those are called varicosities. So in this case, they're releasing neurotransmitter into all different diffuse junctions there. Okay. Calcium binds calmodulin rather than troponin. So calmodulin is just a different molecule that functions in smooth muscle in the same way that troponin did in skeletal muscle. Calmodulin is what activates the myosin filaments. And they're what are called dense bodies that anchor the non-contractile elements to the sarcolemma. And so look in the lower left. The contraction of smooth muscle looks very different than the contraction of skeletal muscle. So remember, with skeletal muscle, we had the sliding filament mechanism, and the whole muscle shortened up as the thick and thin filaments slid past one another. Well, smooth muscle, it's more like, think about taking a washcloth. Let's say a damp washcloth or a wet washcloth that you're trying to wring it out. So, you twist your hands in opposite directions, and you know how the washcloth, kind of bunches up. See, like in the lower left? That's how a smooth muscle contracts. It's a very different looking kind of contraction, okay? So, again, no sliding filament mechanism. Myofilaments spirally arranged, causing the muscle to contract in a corkscrew fashion, which is what I was just describing with the washcloth. Slow contractions that are easily prolonged, and some smooth muscles contract in response to hormones or local chemicals rather than nerves, local chemicals like paracrines. So, a lot of differences between smooth and skeletal muscle. I want you to know the basics of smooth muscle, but it's not a huge topic for us. Really, skeletal muscle is our main topic for this section of the class. Again, just keep track of the basics of smooth muscle and you should be fine. Let's conclude by talking about some disorders of muscles and joints. Just a handful, just to get an idea of some things. So osteoarthritis is the wear and tear arthritis. Basically, everybody gets osteoarthritis. As you get older, your joints degenerate, those synovial joints. The articular cartilage starts to wear down, especially in those weight-bearing joints. And then what can happen is you get, little areas where there's not enough articular cartilage, and so you actually may get bone rubbing on bone. And what does that do? That causes inflammation, doesn't it? And remember inflammation? Remember what's the technical name for a joint? An arthrosis. All right, so if you get inflammation of an arthrosis, you have arthritis. And osteoarthritis is just talking about the fact that this is what happens to everybody. The bones, start scraping on bones. Everybody's going to get this, essentially. The older you get, your joints just wear out. I mean, think about it. Cars don't run forever. Things wear out. All those moving parts constantly moving, they wear down. And the human body is just like that. Eventually, you just wear down. You can't help it. Rheumatoid arthritis is a completely different thing. It's an autoimmune disease. Autoimmune disease, in case you haven't heard about that before, this is where your immune system attacks your own body. Your immune system is supposed to attack foreign invaders like viruses and bacteria, like the coronavirus. But what happens is sometimes your immune system goes wonky and it starts attacking your own tissues. It's like, that's so rude. Immune system, seriously, why would you do that? But it happens. So rheumatoid arthritis is where your immune system, for some reason, starts attacking the connective tissue in your own joints. Oh my gosh, that's really a tragic thing to have happen. And so here you see in the lower right, osteoarthritis. Yeah, the joints start to swell and everything. They get inflamed. But boy, rheumatoid arthritis, you actually start destroying the joints themselves. And this is kind of a tragic thing. The joints just completely deteriorate. So you may have seen people with severe rheumatoid arthritis. They're all gnarled and twisted up, their arms and their hands and their spine. You don't see that as much anymore because now we have very good drugs for rheumatoid arthritis. And most people with RA, as it's often abbreviated, live pretty normal lives. In the old days, though, when I was a little kid growing up, they didn't have those kinds of drugs. And I remember seeing people with, I didn't know what was going on at the time. Looking back now, I'm pretty sure that's what was going on. And really they were. These people were all hunched over and twisted and so on. It's very sad. Good that they've got better drugs for that now. And then gouty arthritis, people simply call it gout, results from a buildup of uric acid in the blood and the deposition of uric acid crystals in the joints. So due to gravity, gouty arthritis, again, people often just call it gout. It happens in the lower extremities. The big toe is a common sight. So uric acid precipitates out of the blood and forms these little tiny knives. So what you do is you get these giant masses of tiny knives that are stabbing in to the joint tissue all around there, and it's extremely painful. They say that people with gout, like, if it's in the big toe, just putting a sheet on top of the foot is enough to cause severe pain. So once again, now gouty arthritis has very good drugs, very simple drugs. So gout is usually not a problem anymore. You just take a drug for it and everything is fine. Myasthenia gravis, an autoimmune disorder that causes progressive degeneration of the NMJ, resulting in a loss of acetylcholine receptors. So here, remember, in order for the neuromuscular junction to work, the neurotransmitter acetylcholine has to bind to the receptors. Well, in myasthenia gravis, the receptors start getting destroyed. So here you got plenty of acetylcholine, but you got no receptors for it to bind to. So what does that mean? It means you can't move. Ptosis is one of the first signs. Ptosis means the eyelids. I'm not sure exactly why. The muscle there is levator palpebris superioris, and I'm not sure exactly why that's one of the first ones affected, but it is. So the drooping of the eyelids. Remainder of the body usually affected within a couple of years. Basically, it gets worse and worse and worse until finally you can't breathe. Your diaphragm, you can't move. You can't move anything. So Aristotle Onassis, the husband of Jackie Kennedy, had that, but of course you have no idea who Jackie Kennedy is. And then finally here, muscular dystrophies, a group of inherited disorders in which there's a breakdown of skeletal muscle fibers. There are lots of different muscular dystrophies. I think the most common is Duchenne's dystrophy. Individuals with these defects with these disorders have defects in the dystrophin, a structural protein. Remember, I mentioned this before, along with myomycin and titin. Dystrophin is one that sort of holds the whole muscle together. And so muscle fibers not held together well may leak substances like creatine kinase, and so eventually you just get severe muscle weakness. That's what the muscular dystrophies are. Okay? Fibromyalgia, very controversial disorder, affects fibrous connective tissues of muscles, tendons, and ligaments, causing tenderness and pain. There have been, a lot of discussion as to whether or not this is a real disorder or not. I think it is. It's probably also very much overdiagnosed. But you'll find lots of, in the self-help section of the bookstore, of course there aren't bookstores anymore, on Amazon, Fibromyalgia, How I Fully Recovered, and it's usually, these books talk about using meditation and a vegan diet and so on, and I don't know. It may all be true, may not be true, but it's probably a real disorder, again, that, you know how there's some people, I'm sure you've known people like this, they wake up every day and they just kind of wait for something to go wrong so that they can tell you about it. You know who I'm talking about? A lot of those people tend to have fibromyalgia. So, again, I'm not making fun of this. I think it's a real thing, but it tends to be overplayed. And shin splints, runners get these, so tibialis anterior, often from running on hard surfaces. I know I used to run cross country in high school, and I hated running on pavement. I always would rather run on ground. There's more give, so always try to run on the ground. I'd rather feel the earth beneath my feet, says the Peruvian folk song. I'd rather be a forest than a street. I'd rather feel the earth beneath my feet. That's the way I feel anyway. Carpal tunnel syndrome. So here we've got a compression of the median nerve. Median nerve runs right down the middle of your forearm. And what can happen is people who do a lot of wrist activity, moving your wrist around a lot, there's the flexor retinaculum, which is a big giant band of connective tissue, and it can get inflamed and press on that nerve. And usually, it's funny, the way it works is you've also got a radial nerve and an ulnar nerve. And the median nerve carries sensory signals from the thumb, index finger, middle finger, and just half of the ring finger. And so it's a really telltale sign. If you get people, you wake up in the middle of the night and you have pain and numbness and tingling in your hand, if it follows that pattern, that's kind of a dead giveaway that it's carpal tunnel syndrome. Now, what can you do for it? Well, kind of a desperate measure is to go in there and cut that flexor retinaculum. It'll relieve pressure on the median nerve, but it'll also lead to weakness. You won't have the same power of flexion you had before. In some cases, that's what you have to do, and I've known people that had that done. They still live relatively normal lives, but they lost a lot of grip strength when that happened. I had carpal tunnel at one point, and fortunately I went to a neurologist, and he diagnosed it and said, yeah, they do this cool thing where they stick these little electrodes into your arms and they generate electricity, and you feel involuntary contractions of your arm, and they do this timing stuff. And he said, yeah, you've definitely got carpal tunnel syndrome, and surgery would be kind of a last resort. I'm going to send you to a physical therapist first. And thank goodness he did, because man, let me tell you, physical therapists know what the hell they're doing. So the physical therapist was great. She started by just interviewing me and asking me what kinds of things I did. And she noticed that I did a lot of typing on the keyboard, that I play the guitar, and that I do a lot of bicycle riding. So what she did was she actually had me bring my bicycle in and show her how I sat on my bicycle and how I held the handlebars. And then she had me bring my guitar in and show me how I sat with my guitar, how I held it, and so on. And she basically recommended changes in the way I rode my bicycle and changes in the way I played my guitar. And you know what? She completely cleared up my carpal tunnel syndrome. So Always give that a try first, kids. Don't go to the desperate measures like surgery. Those physical therapists, they know what the hell they're doing. So we're done. That's it for muscle physiology. You've got your exam coming up.